basically agreed that the next generation of experiments should be fully below this inverted hierarchy band. So either make a discovery in this region or fully rule it out. And so for core A, this means improving our half-life sensitivity by about 2 orders of magnitude. So we want to get down to about here. In order to do this, we have to build a detector that has essentially 0 background in the region of interest. And what this means is if you see a signal, if you see any events at your signal position, they have to be neutrinomless double beta decay, because you can't have any backgrounds. So in order to do that, I need to tell you real quick one fact about our backgrounds in core A, is that the vast majority of our backgrounds come from alpha decays, which occur on surfaces near our detectors. So this is just naturally occurring radioactivity. An alpha decay occurs on the surface, deposits a little bit of energy into some copper, some uninstrumented material, and a little bit of energy into our detector. And so it's really these alpha decays that form the vast majority of our background. So if we can identify alphas, we can get rid of our backgrounds. So this was the idea behind the core A upgrade with particle identification. And if you speak Italian, you know that core A is Italian for heart, and our upgrade is called Cupid. And that's, I guess, supposed to be funny. But anyway, so Cupid is based on the idea that when a particle interacts in our bolometer, it doesn't just produce the heat that we've been measuring out so far, but it also produces a light signature as well. Whether that light is from scintillation or just Cherenkov light, it should produce some amount of light. By measuring both the light and the heat, and then taking the ratio, we should be able to distinguish a beta particle, which is our signal, from an alpha particle, which is our background. And so this is what we intend to do, but in order to do this, we have to be able to measure this light signal. There are many options being investigated in upgrading from core A to Cupid. I will say that Cupid intends to reuse the core A cryostat, so we're not starting from scratch again. We just need to replace the detector that's in there. And we're really developing 2 primary R&D paths. So the first one is developing scintillating crystals and enriched crystals. This is crystals that just emit more light, because more light is easier to see. And the second is, of course, developing the light detector that reads out this light. So fairly straightforward why these are our two main paths. So I really don't have time to get into the details of this. So I have just shown some pretty pictures here. I'll give you a couple of highlights that I'm particularly excited about. So this is a result that came out last October from some of our collaborators. They actually instrumented a full-size core A bolometer with a light detector, and they were able to measure out the Cherenkov light from decays within the bolometer. And what is so impressive about this is that at these energies, there is not a lot of Cherenkov light. You're talking about 10 to 15 or so observable photons. And so you really need a detector that is really sensitive enough to see this. But they were able to do that. They saw, this is their light channel. They saw 2 distinct peaks. This one centered at 0 corresponds to the alpha particles. Alpha particles, of course, don't emit Cherenkov light because they're non-relativistic. And then a peak centered above 0 that corresponds to beta particles. And so by doing this, they were able to separate their backgrounds from signals and reject something like 99.99% of those background alphas, while keeping about 92% of our signal events. So this is a very impressive result. It indicates that we should be able to get down to that 0 background level, and so we were very excited to see this. Something else that I'll briefly mention is we're also developing new thermometry for our bolometers. We're looking into using transition edge sensors. And transition edge sensors take advantage of the fact that a superconductor, its resistivity is very sensitively dependent on temperature as it goes from a normal conducting state to a superconducting state. So in this region, it acts as a very good thermometer. So this was something that I was working on while I was at Berkeley. It's something that I'm interested in continuing to develop in the future. I don't really have time to get into the details of this, but if you're interested, we can discuss later. The last thing that I wanted to mention is that we're not just doing R&D, we're also doing some new physics along the way. So we're working with a company in Massachusetts called RMD, and they grew for us a lithium-indium selenide crystal. That is this thing here that looks roughly like a Jolly Rancher. And lithium-indium selenide could, in principle, be used for a neutrinoless double beta decay search, but it turns out to be not a very good candidate because indium has a naturally occurring radioactive isotope. So if you try to use this, you would just see nothing but the beta decay from indium-115, and indeed, that is what we see. But it turns out that indium-115 beta decay is a fourth-order forbidden decay, which turns out to be particularly sensitive to much of the same physics that our neutrinoless double beta decay searches are sensitive to as well. So if you remember a few slides back, I told you that there was a factor of 2 to 3 uncertainty on those nuclear matrix elements. A very sensitive measurement of this beta decay spectrum helps us shed light on those, on that physics. So indeed, we have measured, we have made the most sensitive measurement of the indium-115 beta decay spectrum to date. We are currently analyzing it. Unfortunately, I can't tell you any numbers, but there is a PhD thesis by one of our graduate students named Alex Later that will be coming out definitely in the summer. So we're very excited about this. So to conclude on the Quarry and Cupid side of this, the main takeaways here is that Quarry is taking data. So far we have begun setting world-leading limits on neutrinoless double beta decay half-life of tellurium-130. Something I really didn't have time to talk about, but is additional physics that we can do. We actually have dark matter searches. We have axion searches. This one is really interesting. If you're interested, we can talk about it afterwards. As well as just normal standard model nuclear physics measurements that we intend to make. So the next 5 years will be really mining the data set that comes out of Quarry and doing a lot of interesting physics there. On the next generation bolometric detector front, Cupid is making good progress towards reaching that zero background level. There is still work to be done to build this up from sort of one-off prototypes to a full ton scale detector. So there's, this is what much of the next 5 years will be spent doing as well. So with that, I'm going to leave behind neutrinoless double beta decay and switch to talking about dark matter. So probably many of you have seen a slide that looks something like this. There is a very good case to be made for the existence of a thing called dark matter in our universe. We have seen the evidence for it in galactic rotation curves. This is basically just galaxies spinning a lot faster than they should be, given the amount of matter we can observe in them. We have seen footprints of dark matter in the cosmic microwave background, and we have seen the effects of it in weak lensing, in clustering, and in strange galactic dynamics. Probably you have seen this picture of the bullet cluster. And what all of this is pointing towards is that there is a significant fraction of the energy density of the universe that we just do not understand and we cannot see. In fact, the standard model that we have spent the last 60 years understanding only accounts for about 15% of the matter density of the universe. The other 85% is this stuff that we know very little about. So what can we say about this dark matter? Well, not a whole lot, unfortunately. We know that it requires physics beyond the standard model. We know that it interacts gravitationally, but past that we don't know much. Does it interact through the weak interaction? Does it interact through an electromagnetic interaction? Is there some kind of new force that it can interact through? In terms of mass of this dark matter, there's actually 70 orders of magnitude in viable mass range that it can work in. There is just, I like this plot because it shows just a huge number of theories that are making predictions about what the dark matter possibly could be, but there is still quite a large region in the middle that maybe it's something we haven't thought of yet. From an experimentalist point of view, a place to start is we typically favor theories that solve more than one problem at a time. So with that, I'm going to make the case for axion dark matter. So it has been known for a long time that the axion is a dark matter candidate, but it was actually originally introduced in order to solve a problem in the Standard Model. And this problem is known as the strong CP problem. The basics of it is that if you write down the Standard Model Lagrangian, you have a term here that violates CP, and in particular, it predicts an electric dipole moment for the neutron. And we have searched for an electric dipole moment for the neutron, and so far we haven't found an electric dipole moment for the neutron. So we can classify the strength of this CP violating parameter in terms of this theta bar thing. And the current limits on it are that this parameter needs to be less than 10 to the minus 10. So the fact that this parameter can take any value between minus pi and pi, but it is so close to 0 such that CP is conserved, is what is called the strong CP problem. To create an analogy, unfortunately I can't take credit for this. This analogy comes from Pierre Sikivi. This would be like walking into a room where the floor is slanted at some angle. It doesn't matter the angle. It could be even 75 degrees. You could be sliding across the room. But in the middle of the room, there is a pool table. And the pool table, despite the fact that the floor is slanted, the pool table is flat. In fact, it is so flat that it is flat to better than 1 part in 10 to the 10. Right? This looks like a very unnatural situation. This looks like this pool table has been tuned to be very, very flat. The most popular solution to this strong CP problem is what is known as the Peccei-Quinn mechanism. And the idea here is to introduce an axion field that has this CP violating parameter. And so what you do in effect is you turn this from a static problem into a dynamic problem. So now the coefficient that sits in front of here can vary. And in fact, this axion field picks up a potential, and not surprisingly, the minimum of that potential sits right at this theta bar value. So even if theta bar is non-zero, even if CP is supposed to be violated, you have this field that just rolls down this potential and cancels out that CP violating term on whole. Right? The entire coefficient that sits in front is actually what goes to 0. So in doing that, we generate a mass for this axion field. And the thing to note here is just that the axion mass is very, very small. So if you're used to thinking of dark matter masses like WIMPs in the range of hundreds of GeV, this is a completely different mass range. In these slides today, I'll be talking about axion dark matter with masses in the nano electron volt range. So this is a completely different mass range. So to jump back to our analogy, what the Peccei-Quinn mechanism does is it turns this from a static problem to a dynamic problem. We take the pool table, we put it on a pivot, and we hang something heavy from the bottom. Right? So even if the pool table started off at some strange angle, this heavy thing would just roll down to the bottom and drag the pool table to be flat. So this may seem like an unnatural way to build a pool table, but at least we have explained why the pool table is so flat. It is very clear why this pool table is flat. Okay, so how do we get dark matter out of this? Well, it turns out that I lied to you a moment ago when I said that the field just rolls down to the bottom of this potential. That's not what a field would do. A field would actually roll down to the bottom of the potential, roll up the other side, stop, come back, and then just sit there and oscillate. In fact, that is exactly what the field does. It sits there oscillating, and the frequency of oscillations turns out to be exactly equal to the mass of the axion. And so this field, which exists at all points in space, occasionally has a potential energy, and occasionally it has a kinetic energy. But this just means that it has an energy density. And it turns out that that energy density throughout all of space acts just like dark matter. It is this signal, this oscillation, that could be creating the dark matter density that we observe today. So how do we go about searching for this? In addition to the field having this CP violating term so that it can cancel the strong CP problem, it also has interactions with the Standard Model. And in particular, the one that we're going to be paying attention to is this axion to two photon coupling. So you can think of this as an axion scattering off a photon to another photon, or perhaps an axion decaying to two photons. The important thing is that the axion couples to the photons. And this creates a new term in your Standard Model Lagrangian. but more importantly, when you chug through all of the numbers, it actually creates a new set of Maxwell's equations. And in Maxwell's equations, you get two new terms. You get a term that looks like this, and a term down here that looks like this. So now you might say, well, we've known about Maxwell's equations for a very long time. Why haven't we seen these terms? And the reason is because these terms are proportional to this GA gamma gamma coupling parameter. And this coupling parameter is expected to be very, very small. So it may very well be that we have just never built an experiment sensitive enough to observe these terms. So the rest of these slides will be how we want to go about building an experiment that is actually sensitive enough to see these terms. So the one of these equations that I'm going to be paying attention to is this bottom one here. And I'm going to take two approximations. First, I'm going to assume that the gradient of the axion field is negligible. This is reasonable because the axion field sort of permeates all of the universe. It varies kind of on galactic distances. Within our laboratory, it's probably constant. So we're going to set this term to 0. Second, I'm going to assume that this dEdt term is 0 as well. And what this is this is the magneto-quasi-static approximation. It means we are assuming that we can have currents and we can have magnetic fields, but we can't have radiation. So that's the limit that we're going to take this. So in this limit, you can write down this del cross B equals a term that looks like this. And so this is a new form of Ampere's law. And if you remember your Ampere's law, you remember that del cross B usually equals a source current. And so we can think of this exactly as a source current term. So what this is telling us is that in the presence of a static magnetic field and a oscillating axion field, remember this axion field is a sinusoidal function of time with a frequency exactly equal to the mass of the axion, you generate an oscillating effective current parallel to the magnetic field. And so this is what we're looking for. So this is the basic idea that underlies the abracadabra experiment. And abracadabra stands for a broadband/resonant approach to cosmic axion detection with an amplifying B-field ring apparatus, which is why we shortened it to abracadabra. But even that's kind of long, so sometimes, usually I'll just call it abra. But the basic idea is you have a toroidal magnet that has a static magnetic field that is going around the toroid, right? And in the presence of an oscillating axion field, this generates an effective current that is parallel to the magnetic field and also going around the toroid. And what the magneto-quasi-static approximation is that we're going to assume that this current has a chance to make a few laps before the axion field reverses and this effective current reverses. And because we have current going around a loop, that generates a magnetic field to the center of the loop. And then when the axion field reverses and the effective current reverses, the magnetic field to the center reverses. So in fact, we have an oscillating magnetic field through the center of the toroid. And so by inserting a pickup loop into the center of this toroid, we should be able to measure the currents that are driven by this oscillating magnetic field. The key is, of course, that these currents are very, very small, so you need a very, very sensitive current detector. And then also this turns out that you need it to be superconducting so that you don't lose it in Johnson noise. But the important thing to note is that because of the symmetry of the toroid, in the absence of axions, the center of the toroid will have no magnetic field. So this is very similar to a low background experiment where you want to build a detector in which there are no magnetic fields in the center of your toroid so that any magnetic fields, oscillating magnetic fields that you do observe will be your axion signal. So this is what a potential axion signal could look like. Essentially what you do is you measure your current as a function of time for a very long period of time. You take a Fourier transform and you will have some noise floor, and this noise floor could come from perhaps your squid. Squids have sort of this noise limit, or it could be thermodynamic limit, but some noise floor, and if you're very lucky it will be flat, and if you're very, very lucky you'll see a peak above the noise floor. And the frequency of this peak will tell you the mass of the axion. So this is what we are searching for. And to do that, we have built a prototype, a small prototype of this experiment that we have called Abracadabra 10 centimeters. We named it 10 centimeters because it is in fact 12 centimeters on each side and has a maximum field of about 1 Tesla. So we worked with a company in Massachusetts to actually build this toroidal magnet. This is the structure of the toroid is made out of 80 of these wedges that when you stack them all together, they make the full 2 pi. And I don't know if you can see this, but between each wedge, there's a set of grooves. And into these grooves, we wind, this is a superconducting wire that carries the DC current that drives our 1 Tesla magnetic field. So this is basically how you make a toroidal magnet. And the toroid is actually wound in 3 pieces. This is what it looks like while it is being wound. And then they are glued and then wound together so that it is one total winding. This is what it looks like when the whole thing is put together. I should say that this is a persistent magnet, so it is cooled down to the stage where it is superconducting, so it needs to be below 4 Kelvin. So we have to wrap it in thermalization straps. I don't know if you can see these red wires that come out. That's the pickup loop that is in the center that we use to measure that oscillating magnetic field. And then the whole thing is mounted in this tin-coated copper shield. And the reason that you coat it in tin, I should say it's coated on both the inside and the outside. The reason that you coat it in tin is because once you get below about 3.5 Kelvin, that tin goes superconducting, and because of the Meissner effect, it does a very good job of shielding your pickup loop from any kind of external magnetic fields. So we then take this thing, this magnet. It's roughly about this big, it weighs about 10 pounds, it's roughly the size of a basketball. And we mount it at the bottom of our dilution refrigerator. So this is a dilution refrigerator that we have at MIT. The base plate of this fridge will get down to about 150 millikelvin. The thing is actually suspended from a Kevlar thread, which to me is kind of amazing. But you can't see on a warmer stage, there are our squid readouts, which are actually read out up there. So we have cooled this thing down. We have taken data with it. This is what our first data looked like. I told you if you're very lucky, it will be flat. This is approximately what my face looked like when I saw it. And it turns out that we have a whole lot of vibrational noise. And this is not surprising. It's a prototype. We're learning as we go. Vibrational noise was kind of expected because if you look outside our lab, there is actually a construction site, and to first order a construction site is really just one great big noise generator. And so we actually spent some time installing a new detector suspension system. And what's kind of neat about this is we're suspending the whole thing from about a 2-meter pendulum that's attached to a spring that's attached at 300 Kelvin, and then we try to cool this thing down to 100 millikelvin. So it's interesting. It has actually worked. We're just now got cold, I think, today. So we're going to start testing out how this worked. So that's exciting. Okay. So where does the abracadabra sensitivity lie in the sort of parameter space of axion searches? So this is what the parameter space looks like. This is the axion mass on the x-axis.